Here we have a ladder that's resting on the floor and leaning up against a wall. So here's the ground or the floor, here's the wall, and here is our ladder leaning against the wall. The ladder has a length of 3 meters and a mass of 10 kilograms. We have a person with a mass of 80 kilograms climbing up the ladder. And let me just point out, the ladder makes an angle of 50 degrees with the ground. There's also some friction between the ground and the ladder. Well, there's a coefficient of static friction of 0.150. Before I ask a question about this, let's start on the free body diagram. Let's draw in the forces acting on the ladder, and that will lead us to our question. What forces are acting on the ladder? Well, we know that the ladder has a weight, so there's the weight of the ladder. Where does the weight of the ladder act? At the center of the ladder. So at the center of the ladder, I will draw in the weight of the ladder. So, whoops. And what's the direction of the weight of the ladder? Straight down. So I'll label this as W sub L. What else? Well, there's the weight of the person. The person is standing on the ladder, the weight of the person. Where does that act? That acts at the point where the person is standing. In what direction? Straight down. So we've got a force acting down. I'll call this W sub P for the weight of the person. What else? Well, the ladder is resting on the ground. We're going to have a normal force. So the ground is going to push upward on the ladder. Where does that force act? That acts at the point where the ladder touches the ground. So I will draw in a force upwards. We'll call this, we'll call this F sub G. In other words, the force from the ground. So here I'll write F sub G, the force from the ground. What else? Well, there's some frictional force. What direction is the frictional force? If we think about this ladder leaning against the wall, if there were no friction, what would happen? The ladder would slide out this way and fall. So the friction must be pushing on the ladder this way to keep it from sliding this way. The force, the frictional force, must be to the right. Where does it act? It acts where the ladder touches the ground. So we must have a frictional force acting at that point to the right, in other words, towards the wall, and we'll call this F sub S for the static frictional force. What else? Well, the ladder is leaning against the wall, so the wall must exert a force on the top of the ladder. What's the direction of that force? This is a very interesting question. We know the ladder must, we know the wall must be pushing back on the ladder this way. So we know there's going to be at least some force pushing to the left. So I'll put in that force like this. I'll call this F sub W. In other words, the force from the wall. But what about up and down? Well, if there were some friction between the ladder and the wall, then there could be an up or down force from friction. This actually gives us a bit of a problem. If we include friction from the wall, then we do not arrive at a single unique solution to this problem. This is something we haven't run into before. If we include friction from the wall, there is not a single answer to the problem that I'm going to ask about. In order to make sure that we have what's called a unique solution, in other words, one single solution, we are going to choose to assume that there is a frictionless connection between the ladder and the wall. We're going to assume that's a frictionless surface. If you're interested, I would definitely suggest trying to solve this problem and include some friction from the wall and see what happens. See if you could do it. It's actually a very, very interesting problem, but not one that I want us to have to deal with at the moment. There we go. Those are all of the forces acting on the problem. Now here's what I want to get at. Here's the question. As the person goes up the ladder, as the person walks up the ladder, climbs up the ladder, more and more friction is going to be required from the ground. Let's imagine that the person has gone so far up the ladder that we have as much friction as can possibly be exerted by the ground. What's the maximum amount of friction that can be exerted? What's the maximum value of static friction? Fs max. So I want to assume that the person has gone so far up the ladder that the person has gone as high as possible. If this person were to go any higher, there is not enough friction that can be exerted on the ladder, and the ladder would slide out. So we're going to assume that the amount of friction being exerted is Fs max. And the question is, how far up the ladder can that person go to get that amount of friction? What's the maximum height the person can go? So we will assume that this person is some distance d from the ground, and that's the question. What is d? We couldn't really understand what the question was until we started to think about the forces and realized that there was a maximum distance that's going to maximize the amount of friction that we have. That's the question. There we go. Let's take a look at those. Let's stick some numbers in and see what we get. We have that the weight of the ladder is the mass of the ladder times g, 10 times 9.8, or 98 newtons. And the weight of the person, again, mg, 80 kilograms times 9.8. That gives us the weight of the person is 784 newtons. Again, we will just choose our usual orientation for x and y, x pointing to the right and positive, y pointing up as positive. So what do we get for our force equations? F sub x. What forces are acting in the x direction? Well, we've got Fs max, so we have Fx equals Fs max. And then we have the force from the wall, but that is in the negative x direction, so we have minus Fw. Those are all the forces in the x direction, so those must equal 0. Bringing this to the other side, we have Fs max equals the force from the wall, Fw. What about the forces in the y direction? What forces do we have in y? Well, we have Fg, the normal force from the ground, so Fy we have Fg. Then we have the weight of the person that is acting down. The weight of the person we know is 784 newtons. So we have, whoops, actually I put in, sorry, the weight of the ladder first. The weight of the ladder, which is 98, and that's downward, which is negative. So we have minus 98 newtons. And then the weight of the ladder, minus 784 newtons. And again, those are all the forces in the y direction. And so those must equal 0. Bringing these to the other side, we have the normal force from the ground, F sub g, is 882 newtons. But now we can actually figure out what Fs max is because we know the maximum static frictional force is mu times the normal force, and the normal force is this F sub g. So Fs max is mu s Fg, or 0.150 times 882 newtons, which gives us Fs max is 132 newtons. That is equal to Fw, and so we know that Fw also 132 newtons. As a matter of fact, this then has given us, and these two, all of the values of the forces. We know the numerical value for every force. However, we still don't know how far up the ladder the person could go that will then give us that maximum static frictional force. To do that, we need to look at the torque equation. To solve for the torques, what do we have to choose? We have to choose the location of the origin. Where shall we put that? Where do we want to put the origin? We can put it anywhere we want. Well, let's notice. There is a point where not only do we have a force act, but we actually have two forces acting. Where are two forces acting? At the ground. If we choose our origin at the ground point, where the ladder touches the ground, that will remove two forces from our torque equation and just make it easier to solve. Let's do that. Let's choose our origin to be at the ground, and that will remove not only the Fs max, but F sub g from our torque equation. Just let me make one comment about this. You wouldn't want to do that and remove one of the things you're looking for, or if it's the only thing you're looking for. You wouldn't want to remove the only force from your torque equation if that's what you're looking for, if that force is what you're looking for. But if it's not, then removing it and making the torque equation simpler might be exactly what you do want to do. So for us, yes, let's choose it here because we're not looking for either of those forces. Let's choose the origin there and set up our torque equation. I'm going to have to erase this and use just about this entire space for that. So let's do that.